Welcome. Today we are going to discuss our 7th chapter and the only module of this chapter. In this we shall discuss the inverse function theorem and implicit function theorem. All of us are familiar with the concept of inverse function, but we have to keep in mind in this case we are concentrating only those functions which are differentiable. We start our discussion from implicit functions. Let us consider an equation of the type fxy equal to 0. We consider the problem to decide whether this equation determines y as a function of x, say y equal to gx. In such case, we say g is implicitly described by the form fxy equal to 0. As for example, let us consider the equation of the unit circle given by fxy equal to x square plus y square minus 1 equal to 0. We have drawn the circle here. First, let us consider the point A whose coordinates are 1, 0. If we consider a very small neighborhood of x equal to 1 and y is equal to 0, we find that for x less than 1 but close to 1, we can find y satisfying fxy equals 0. But we can find two solutions for y. Those are given by y equal to plus minus square root of 1 minus x square. Due to lack of uniqueness, we cannot express y as a function of x. We observe here del f del y is equal to 2y. So, the value of del f del y at the point 1, 0 is 0. Now, we consider another point on the same circle where y is greater than 0, say x 0, y 0 lying in the first quadrant. Then we find that given x close to x 0, we can find only one y satisfying fxy equal to 0. This is given by y equal to square root 1 minus x square, obviously non-negative. However, one can raise voice for the solution y is equal to negative square root of 1 minus x square, but it lies far away from the point x 0, y 0. And here we notice that the value of del f del y at the point x 0, y 0 is 2 y 0, which is obviously non-zero. The above two observations provoke us to consider neighborhood of points a b such that del f del y at a b is non-zero. This will allow us to express y as a function of x. We start with this assumption. The problem turns out a little more complicated when we consider a system of several equations involving several variables. Our aim is to express some of these variables as functions of the remaining others. We shall find that in such cases the Jacobian determinant plays an important role. We shall start our study with inverse function theorem. We are familiar with the notion of inverse function of a given function, but here we deal with differentiable functions and our concentration will be on differentiability of inverse functions of given functions. We are now going to state inverse function theorem. Before that, we state and prove a lemma. Let A be an open rectangle in Rn and f from A to Rn be continuously differentiable, that is of class C1. Also let f1, f2, fn be the components of f. If the modulus of all the partial derivatives del fi del xj, where ij runs over from 1 to n, are bounded by a quantity capital M over the set A, then for every y and z from A, norm of fy minus fz less or equal to n square m norm of y minus z. We start the proof. Let y equal to the n tuple y1, y2 up to yn and z equal to z1, z2 up to zn. Y and z be arbitrarily chosen from A. Now the set A is rectangular in shape and hence convex. We plan to reach y starting from z through the line segments parallel to the coordinate axis and evaluate the difference of values each scalar field Fi assume at the ends of each segment. We can easily recall that we used such treatment while we were trying to find out differentiability of a scalar field. We find Fi y minus Fi z, that is Fi y1 y2 yn minus Fi z1 z2 zn. We are writing this as follows. At first, we replace in the first quantity yn by zn. So, we write Fi y1 y2 yn minus Fi y1 y2 yn minus 1 zn. At the next, we replace yn minus 1 by zn minus 1. So, the second term looks like this, plus Fi y1 y2 yn minus 1 zn minus Fi y1 y2 yn minus 2 zn minus 1 zn. We continue this process. So, the last one will be Fi y1 z2 up to zn minus Fi z1 z2 up to zn. All the items are written in pairs, and if we find the points under consideration lie on a line segment which is parallel to a coordinate axis. Now, we are using mean value theorem. So, this we can write as yn minus zn del Fi del xn y1 y2 yn minus 1 wn plus yn minus 1 minus zn minus 1 del Fi del xn minus 1 y1 y2 wn minus 1 zn. We continue this. So, the last term will be plus y1 minus z1 del Fi del x1 w1 z2 z3 up to zn. In the above discussion, for each I from 1 to n, wi was a point on the line segment joining y1, y2, yi minus 1, yi, zi plus 1 up to zn and y1, y2, yi minus 1, zi plus 1 up to zn. As a result, we find modulus of Fi y minus Fi x equals modulus of sum of yj minus zj del Fi del xj y1 up to yj minus 1 wj zj plus 1 up to zn. We use triangle inequality repeatedly. So, this quantity less or equal to summation j equal to 1 to n modulus of yj minus zj del Fi del xj y1 up to yj minus 1 wj then zj plus 1 zn. This equals summation mod yj minus zj mod del Fi del xj y1 yj minus 1 wj zj plus 1 zn. This less or equal to summation j equal to 1 to n norm of y minus z modulus of del Fi del xj y1 up to yj minus 1 wj zj plus 1 up to zn. Here we have used the fact that for each j, norm of y minus z greater than equal to mod yj minus zj. So, from the above we find that mod of Fi y minus Fi x less or equal to nm mod of y minus z. This implies norm of Fy minus Fz less or equal to summation I equal to 1 to n mod Fi y minus Fz, and this is less or equal to summation I runs from 1 to n nm mod y minus z, which is nothing but n square m mod y minus z. This completes the proof of the lemma. Let us now state and prove the inverse function theorem. Let a map f from Rn to Rn be continuously differentiable on an open set containing a point A, and determinant of f dash A is non-zero. then there exists an open set V containing the point A and an open set W containing the point Fa such that the map F from V to W has a continuous inverse F inverse from W to V which is differentiable. Moreover, for all y in W, derivative of F inverse at y equals inverse of the map F dash F inverse y. Proof. We first recall that any map which can be considered as a restriction of a linear transformation on an open set is differentiable. Moreover, over that open set it coincides with its derivative map. Let us denote f dash a by t. By proposition, determinant of t is non-zero. Hence, the map T is non-singular. As T is non-singular, its inverse map T inverse from Rn to Rn exists and is linear. Consequently, T inverse is differentiable. Hence, by chain rule, the map T inverse compose F from Rn to Rn is differentiable. We also notice that the derivative of T inverse compose F at A equals derivative of T inverse at Fa composition F dash A applying chain rule. Now, T inverse is linear, so its derivative is nothing but itself. So, we have this equals T inverse compose F dash A as T inverse is linear. So, this equals T inverse compose T as T equal to F dash A. So, this is nothing but the identity map I on Rn. Next, let us assume that the proposition is true for the map G equal to T inverse compose F. This means the following. Let G equal to T inverse compose F be continuously differentiable at a point B and let determinant of G dash B is non-zero. Then there exists an open set V dash containing B and an open set W dash containing GB such that G from V dash to W dash has a continuous inverse G inverse from W dash to V inverse which is differentiable and derivative of G inverse at B equals with the inverse of G dash G inverse B. From the above relation, we find the following by some calculations. Derivative of G inverse at B equals inverse of G dash G inverse B. Now, G dash equal to T inverse compose F dash is the identity transformation. So, the left hand side equals with inverse of G inverse compose B. Now, G is T inverse compose F. So, G inverse is nothing but F inverse compose T. We apply. So, the left hand side turns into derivative of F inverse compose T at B and this equals inverse of F inverse compose T at B. Over the left hand side we apply chain rule. So, we get F inverse dash TB compose T dash B equals inverse of F inverse compose T at B. This means derivative of F inverse at TB compose TV equals inverse of F inverse compose F dash at B. So, this gives F inverse dash TB equals inverse of F inverse compose F dash at B composed with inverse of TB. So, this gives inverse of T compose F inverse compose F dash at B. So, from this finally we get F inverse dash F dash B equals with inverse of F dash compose F inverse compose F dash B. In the above relation we put y is equal to F dash B. So, the above relation becomes derivative of F inverse at y equals inverse of F dash F inverse y. This shows that if we assume that the proposition is true for the map G equal to T inverse compose F, then it is also so for F. Hence, it is sufficient for us to prove that the proposition is true for the map G. Next, we assume that F inverse is differentiable. We use the symbol I to denote the identity transformation on Rn. Clearly, I inverse is I, and since these are linear transformations, they coincide with their derivatives. We use chain rule and hence we find I dash equal to I. This implies F inverse compose F dash A equal to, applying chain rule, this becomes F inverse dash at F A composition F dash A. This equals with the identity transformation. So, this means F inverse dash at F A equals inverse of F dash A. In the above, we again put F equal to Y. So, we find that derivative of F inverse at Y equals inverse of F dash F inverse Y. This is the desired relation. So, without loss of generality, we may assume that T is equal to I. Next, let us assume, if possible, that there exists H sufficiently close to the origin satisfying F of A plus H equal to F A. Then we find that norm of F of A plus H minus F A minus T H divided by norm H equals norm of T H by norm H. We assume T equal to I. So, this becomes norm H by norm H, which is 1. Clearly, this contradicts the differentiability of F at the point A, since we have limit H tending to 0 norm of F of A plus H minus F A minus F dash A operated on H by norm H equals 0, because T is nothing but F dash A. This means that we can find a closed rectangle R1 in Rn such that A from interior of R1 and X from R1 deleted the point A implies Fx different from Fa. We know that a determinant function is continuous and it is nothing but a polynomial. Hence, using neighborhood property, we can find a closed rectangle R2 such that A belongs to interior R2 and X belongs to R2 implies determinant of F dash X is non-zero. Since F is continuously differentiable at the point A, for all ij running from 1 to n, del f I del xj's are continuous at that point A. As a result, we find that x approaches A implies del f I del xj at x approaches del f I del xj at A. This implies modulus of del f I del xj at x minus del f I del xj at A approaches 0 from the right. So, we can find a closed rectangle R3 such that A is in interior R3 and x belongs to R3 implies modulus of del f I del xj at x minus del f I del xj at A less than 1 upon 2n square for every ij from 1 to n. Let R equal to intersection of the rectangles R1, R2, R3. Since all these three are closed, it follows that R is a closed rectangle in Rn with the point A in its interior. This happens because A was an interior point for all the closed rectangles R1, R2, R3. We define a function capital F by capital Fx for fx minus small x for every suitable x. We know small f is continuously differentiable, so capital F is also. Thus, the partial derivatives del f I del xj x are continuous at the point A. Without loss of generality, we can assume that for all x in interior of R, del f I del xj at x minus del f I del xj at A, its modulus is less than 1 upon 2n square. Consequently, for every arbitrary x1 and x2 from R, norm of fx1 minus fx2 less than n square multiplied by 1 upon 2n square norm of x1 minus x2 by the lemma we have proved just. This gives norm of fx1 minus fx2 minus x1 plus x2 less than half norm of x1 minus x2. Thus, norm of x1 minus x2 equal to norm of fx1 minus fx2 minus x1 plus x2 minus fx1 plus fx2. Applying triangle inequality, this is less or equal to norm of fx1 minus fx2 plus norm of fx1 minus fx2 minus x1 plus x2. This implies norm of x1 minus x2 minus norm of fx1 minus fx2 less or equal to norm of fx1 minus fx2 minus x1 plus x2, and this is less or equal to half norm of x1 minus x2. This gives norm of x1 minus x2 less or equal to twice norm of fx1 minus fx2. Now, the boundary of R is a compact set. Since compactness is preserved by continuous map, it follows that f of del R is also compact. Now, A was an interior point of the set R, so is not a point of the boundary of R, and x is from the set R, the point A deleted implies fx not equal to fa. It follows that fa is not in f del R. Hence, we can find a positive small r satisfying R equal to infimum of norm of fx minus fa, where x is from del R. Let W denote the open sphere in Rn with center at fa and radius r by 2. Now, clearly for any y in W and x in del R, norm of y minus fa is less than r by 2. Also, norm of y minus fx greater or equal to norm of fx minus a minus norm of fa minus y, and this is greater than r by 2. This gives norm of y minus fx greater than norm of y minus fa. Let y0 be an arbitrary but fixed point from the set W. We shall now show that it has a unique pre-image in interior of R corresponding to the map F. Let us consider the map small l given by small l x equal to norm of y0 minus fx square. The continuity of small l follows from the continuity of F. Since R is a compact set, L is bounded on R and it also attains its minimum of R. Also, x belongs to del R implies norm of y minus fa less than norm of y minus fx for every y in W. This implies norm of y0 minus fa less than norm of y0 minus fx. We square sides and we find that this implies La less than Lx. Therefore, the minimum of L does not occur on del R. So, there exists a point x0 in interior R such that del L del xj at x0 is 0 for every j equal to 1 to n. This implies summation I equal to 1 to n twice y0y minus fi x0 del fi del xj at x0 is 0 for every j. Since the determinant del fi del xj x0 is non-zero, we have y0y minus fi x0 is equal to 0, and this is true for every I. Therefore, y0 is nothing but fx0. This proves the existence of pre-image of every element of W corresponding to the map in interior R. The next task is to prove the uniqueness of such x0. Let us assume, if possible, we can find x0, x0 dash both from interior of R satisfying fx0 equal to y0 is equal to fx0 dash. Then we find norm of x0 minus x0 dash less or equal to twice norm of fx0 minus fx0 dash. This equals twice norm of y minus y, that is 0. So, this gives x0 equal to x0 dash. This proves the uniqueness. Our next target is show the continuity of F inverse. Let V equal to interior R intersection F inverse W. Then we have proved the existence of F inverse from W to V. Let y1 and y2 be arbitrarily chosen from W. So, there exists x1, x2 in V such that fx1 equal to y1 and fx2 equal to y2. And different y1 and y2 gives different x1 and x2. Now, norm of x1 minus x2 less or equal to twice norm fx1 minus fx2. In other words, norm of f inverse y1 minus f inverse y2 less or equal to twice norm of y1 minus y2. So, y1 approaches y2 implies norm of y1 minus y2 approaches 0 from the right. This implies f inverse y1 minus f inverse y2's norm approaches 0. So, this proves the continuity of f inverse. Now, the final step. In this we are going to prove the differentiability of f inverse. Let x in V. Since the map f is differentiable at x, there exists a linear transformation mu equal to f dash x from Rn to Rn such that for suitable h in Rn, we can express f of x plus h minus fx equal to mu h plus norm h exh, where h tends to theta implies exh tends to theta. One can easily recall here mu is a linear transformation and exh is called the error term. Let us denote phi h equal to norm h exh. This gives f of x plus h minus fx equal to mu h plus phi h. So, we can write mu inverse f of x plus h minus fx equals mu inverse mu h plus phi h. Now, mu was a linear transformation, so mu inverse is also. Applying the linearity of mu inverse, we can write this as h plus mu inverse phi h. Moreover, as h tends to 0, phi tends to the origin faster than h. Since every element of W has a unique preimage in V, let f inverse y equal to x and f inverse y dash equal to x plus h. Thus, the above expression can be re-expressed as follows: mu inverse y dash minus y equal to x plus h minus x plus mu inverse phi of x plus h minus x. This equals f inverse y dash minus f inverse y plus mu inverse phi of f inverse y dash minus f inverse y. This implies f inverse y dash minus f inverse y equals mu inverse y dash minus y minus mu inverse of phi f inverse y dash minus f inverse y. So, our claim will be proved if we can show that limit y dash tends to y, norm of mu inverse phi f inverse y dash minus f inverse y by norm of y dash minus y equal to 0. Now, mu inverse is a linear transformation, so it carries the 0 vector to the 0 vector. So, we have limit y dash tends to y, limit y dash tends to y, norm of phi f inverse y dash minus f inverse y by norm of y dash minus y equal to 0. Now, we notice that norm of phi of f inverse y dash minus f inverse y by norm of y minus y dash. We can express this as product of two terms. First one, norm of phi f inverse y dash minus f inverse y by norm of f inverse y dash minus f inverse y multiplied by norm of f inverse y dash minus f inverse y by norm of y dash minus y. So, this is less or equal to twice norm of phi f inverse y dash minus f inverse y by norm of f inverse y dash minus f inverse y, because we have earlier proved that the second term is bounded by 2. As y dash tends to y, f inverse y dash tends to f inverse y by continuity of f inverse. So, phi of f inverse y dash minus f inverse y tends to 0 faster than f inverse y dash tends to f inverse y. Thus, we have limit y dash tending to y norm of phi f inverse y dash minus f inverse y by norm of y dash minus y equals to 0. This shows the differentiability of f inverse. Clearly, derivative of f inverse at y is mu inverse. Thus, inverse of f dash x equals to mu inverse equals to derivative of f inverse y. That is, f dash f inverse y, its inverse equals with derivative of f inverse at y. This completes the proof. So, we have studied inverse function theorem. In different book, we can find different approaches. We followed the approach found in the book authored by Michael Spivak. Now, we shall use inverse function theorem to prove implicit function theorem. You can find in some books they first proved implicit function theorem, and with the help of that they proved inverse function theorem. Now, we shall state and prove the implicit function theorem. The statement is as follows: let f from Rn cross Rm to Rm be continuously differentiable in an open set containing a point AB. Here A is from Rn and B is from Rn. We further assume that first, f vanishes at the point AB. Secondly, determinant del fi del x n plus j AB is non-zero for all I and j running from 1 to m. Then there exists an open set A in Rn containing A and an open set B in Rm containing B, such that for all x in A, there exists unique y in B such that fxy equal to 0. If we define y equal to gx, then g is differentiable. Proof: we define a map f from Rn cross Rm to Rn cross Rm by fxz equal to x small f x z. Since small f is continuously differentiable, capital F is also. Now, for all every k from 1 to n, we find that del fi del x k is Kronecker delta I k, and for all k equal to 1 to m, del fi del x n plus k equals del fi del x n plus k. Thus, determinant of del fi del x n plus k at AB equals determinant of del fi del x n plus k at AB, and that is non-zero. Hence, by inverse function theorem, there exists an open set W subset of Rn cross Rm containing capital F f b and an open set V subset of Rn cross Rm containing the point AB, such that f from V to W has a differentiable inverse, say capital F inverse. As V is an open set containing AB, we can always find an open rectangle H subset of V containing AB, and we can express H equal to A cross B, where A is an open rectangle in Rn and B is an open rectangle in Rm. Now, capital F AB equals A small f AB, so this equals A0. Let small h be the restriction of capital F inverse over Fh and P be the restriction of F over H. Let Fh equal to U. Thus, we find that there exists an open set H equal to A cross B in Rn cross Rm such that P from A cross B to U has a differentiable inverse H from U to A cross B. We can express Hxy equal to x alpha xy for some differentiable function alpha. Let pi from Rn to Rm to Rm denote the natural projection map defined by pi xy equals y for every x in Rn and y in Rm. It is obvious that pi compose capital F is small f. Thus, small f x alpha xy equals f compose h xy. This equals pi compose f compose h xy. So, this is pi compose f compose h xy, that is pi xy, and it is nothing but y. Thus, f of x alpha x0 is 0. So, we can define gx as alpha x0. This is the desired function. So, in this module we have stated and proved both inverse function theorem and implicit function theorem. With this chapter as well as this paper comes to an end. Wish you all the best.